Hello, everyone. Welcome to session 12, Emerging Technologies in Mobility. Thank you for joining us today. To briefly introduce me, my name is Jahedul. I am an adjunct faculty in the School of Planning at Dalhousie University, all the way in East Coast, Canada. And I'm also a transportation engineer with the Public Works Nova Scotia. And I will be chairing the session today. As you can see on the screen, we have 6 fantastic presentations scheduled for this session. However, our second presentation will not be happening today because Dr. Ubo Jiao will not be able to attend the session, as well as we don't have any recording. So we'll skip these presentations. That gives some extra time to other presenters. So we have 5 presentations. Each presenter can have a time around 24 minutes for their presentations. And I request everyone please to ask your question in the chat box. So our speakers will give a talk today on different topics, such as rail track detection using deep learning models, machine learning in built environment to understand built environment influences in 15-minute city concept, as well as other presenter will be talking about unmanned aerial vehicle operation for last mile delivery, and as well as what will be the future for electric vehicle takeoff and landing aircraft. And our last presentation will be on air mobility influences on the relocation decisions. Our last presentation will play a recording as the author Ningze Ju will not be able to present. However, their colleague Javier will be here to answer any question that you may have. So without further ado, I would like to invite our first presenter, and I'm assuming the first author of the study, Anil Khan, will be the presenter for this for the presentation feasibility of track fault detection using deep learning models.
Hi.
Hi, feel free to share your screen.
Yes, 1 second. Sorry, I need to give access to Zoom. 1 second.
I think you can share your screen now.
Okay. I need to reopen Zoom for access. If you can wait 1 second, sorry.
Hey, Lynn, can you share the image of all the talks that are coming?
Yes, so one presenter, he wants to share his screen for his presentation. Now we are waiting for him.
Oh, got it. Sorry. I'm just jumping out of the main session there that I was moderating. So Anil is your first presenter.
Yep, here you go, Olin. Yep.
Hi, Jahed. Thank
Hi.
you.
Thanks for coming.
So Lynn will make all presenters co-hosts so that you won't lose time on that.
Anil, if you need some more time to set up your mic, we can go with, oh, here you go. Okay. You are muted.
Hi. Can you hear
We can
me?
hear you.
Okay, sorry. Can you see my screen?
Yes.
Is it the presentation mode or the
it looks perfect.
presenter mode? Okay, thank you. Hello all, I'm Anlishan and I'll be presenting our paper on feasibility of track fault detection using deep learning models. The presentation will be in 4 parts: introduction, materials and methods, results and discussion, and conclusion in the end. Defections on track rails can cause major accidents like derailments or collision that cost lives and financial damages. As you can see here on this pie chart, accidents in Turkey between 2019 and 2023 were majorly derailments. And as you can see here on this bar graph taken from another study, derailments are majorly track related rather than equipment related with blue lines. And here taken from another study about derailment causes, the major cause of derailments were broken rails and melts, and some other track-related faults. That's what we need. We want to classify with artificial intelligence in this study. Here are some more statistics about railway accidents that are related to problems that can be solved with better track fault detection systems like using artificial intelligence. You can see here in the past 15, 16 years in Turkey, derailments were the major cause of accidents in railways. These are similar studies on track fault detection using computer vision. Computer vision basically means using assistance of computers with images. Uh, Defections can be classified in several different ways. We used in the study UIC classifications, UIC International Union of Railways. We use 712 and 725 classifications. 712 classification classifies defections based on where they occur, like rail ends or welds, and their orientations, like horizontal or something else. But 725 classification classifies defections based on their severity rather than their types. Here are some examples of different defection types, their OIC 712 codes, names, and images. Cracks, corrugations, shellings, wheel burns, these are all visible to naked eye, so they can be identified using images, so therefore they can be identified using AI systems. And all these defection types are present in the data sets we use. The second section is materials and methods. In this section, I'll briefly mention what are AI, machine learning, and deep learning are. I'll then introduce the models and the dataset we used. The three models we used three deep learning models. These are Inception model developed by Google, ResNet model developed by Microsoft, and VGG model developed by University of Oxford. The workflow of a study like this goes something like the first we collect the data from railroads. This can be taken with a camera or with hand manually walking alongside the roads. Then we validate data. We eliminate the not useful ones. Then we take the useful images and separate them into three sets: training set, validation set, and test sets. Then we train the model and evaluate its performance based on some functions. The functions used in the study are categorical accuracy, sparse accuracy, precision, and area under the curve functions. I like to mention some terms now used repeatedly in this study. As you can see here on this image on top right, there are three sets present: training set, validation set, and testing set. Training set makes up 70 to 80% of the data. Validation set makes up 10 to 20% of the data, and the testing set makes the last, the smallest set. Training happens between epochs, like every one iteration called an epoch in machine learning. The same images are shown to the model over and over again. If the model sees same image or same kind of image less than it should, it doesn't learn anything. Here you can see over this image, it doesn't learn any good patterns. That's called underfitting. We don't want that. On the other hand, if the model sees the same images over and over again, it it memorizes it rather than learn patterns from it. It memorizes. So we were make careful to be sure we didn't do underfitting or overfitting. Now, if we talk about the data, there are two data sets taken from two different studies. One data set has only defective and non-defective labeled images. The second data set has only defective images. It doesn't have any non-defective images, but they are labeled with their defection types. The first dataset is collected in Bangladesh railroads manually. It has 384 images. 78% of these images are in training set, 16% in validation set, and the rest are in testing set. The second data set, the data is collected in Pakistan railroads with a camera mounted on a railway inspection vehicle, taking photos 120 frames per second. But here, as you can see, this is a much bigger data set compared to the first one. But some of the defection types are overrepresented in the data set. We don't want that. That would cause overfitting for those defection types. So we use similar number of images for all of the defection types. After the training, validation, and testing the data, it is time to look at the results and evaluate them. In this chapter, we'll first look at the performance of each model in each dataset, two datasets, three models. Then we'll compare the results with each other. The first task is identifying images on the first dataset. If you remember, it had only defective and non-defective labeled images. Loss graph, we care about two parameters in this study, loss values and accuracy. We want loss value to be close to zero as much as possible. Without being zero, that will mean overfitting. The same goes for accuracy. We want it to be as high as possible without being 100%. The first model, Inception, had 81% accuracy on the first task. The second model, VGG16 model, had a better accuracy on validation set, and we care about validation sets accuracy more than we care about the training sets. As you can see here, loss graphs looks way more smoother than Inception models. So we can say VGG16 model performed better in this task with a higher accuracy and lower loss value. If you look at the last model, resonant model, it had a similar percentage of accuracy and similar loss value. They are a bit lower, but we can say it performed better than Inception model. If we look at them all at once, we can clearly see which model performed the best in first task. And here are the numbers. We can see resonant model following VGG model closely, but not quite on the same level, while Inception model performed poorly compared to rest. Now we'll talk about their performance on the second dataset and to see if this performance rankings, VGG being the best, Inception being the worst, and their accuracy and loss values are carried. Now we are looking on the second data set. It had 7 labels, each for each defection type, instead of just 2, defective and non-defective. So it is harder for the models to classify them just out of the box because there are more to choose from. We can see accuracy dropped to around 70%, 69% for Inception model, with a much higher loss value. The second model, if you remember, VGG model was the best one and Inception model was the worst one. But on second test, they have pretty similar accuracies, 69%. But VGG model has a slightly better loss value. So we can still say VGG model performed much better than Inception model, but not as much like it was on the first task. The last one, the ResNet, has a better accuracy on the validation set than the other two models, but it also has the worst loss value. So if you look at the graphs like this, you can see graphs look a lot more rougher than for the second task rather than it looked on the first task. And accuracies dropped a bit much. Even if it's okay for the validation set, 88% are good accuracies, but same cannot be said for 70% because this is an important matter. Just I showed earlier slides, it causes derailments on other accidents. And if you look at the model's performances together in the end like this, as you can see, the best performant model for the first data set was not the best performant model for the second data set. This means if we mean to use these methods, artificial intelligence with railroads, it's important what we are trying to do. Are we trying to identify defections or are we trying to classify them? Just because a model or artificial intelligence in general is good at doing something, it doesn't mean it's good at everything in this kind of thing. Because 91% accuracy is okay and acceptable in my opinion, but same cannot be said with 72% accuracy. Okay, it was this much.
All right. Thank you, Anil,
Thank you.
for the
Thank
excellent
you.
presentation.
Okay.
Is there any question in the chat box? Okay. Any question from the audience? Okay. I
Okay,
might have a
thank you.
question for you.
Okay.
So as this is kind of using image data in the model to identify the defection in the rail track. So is there any resolution constraint or what kind of quality we are looking for the image data? Is there any special instrument that you have to use to collect those data?
Yes, like I said in dataset 2, if we use cameras and manual take, in dataset 1, the images are taken manually, meaning people literally went on the roads, railways, and took images for them in the first study taken this data set is from. That would mean nothing in production because it will just be as some workers looking with their own eyes rather than using intelligence. But in the second data set, in this study, they used a camera mounted on a rail inspection vehicle, and vehicle goes, I believe it's around 30 miles per hour or kilometers. I'm not sure actually, but that would mean it's a lot faster than manual inspection. And the accuracy means how reliable it is. It's a lot cheaper and a lot faster, and we wanted to see if it's reliable in this study.
All right. Okay. I think we have a
Okay.
question in the chat box. False negatives and false positives are not equally problematic in this context. False negatives are much more worrisome. Did you analyze the frequency of false negatives?
I don't think so. We did not look at p-values and false negative in this study, no.
Okay, but is it possible to do that within the model?
I think so, yeah, I think it's possible.
All right. Any further question? Yeah, so I have another question you can even answer in the chat box. If your model can determine the severity of the defection. So to prioritize a section of rail for maintenance, and also can we use the similar approach for pavement crack detection or something like that?
I think it can be used for payment too. I think it might be even better for payment because in railways there are a lot of cracks happening inside the rails, so it's not visible. Of course, since we use images, we can only detect defections that are visible to naked eye. And payments are most likely to be visible, I think. Railways have cracks inside or that cannot be seen with because you mount a camera on an inspection vehicle, it can only see from one angle. So you can only detect those cracks. I think payments can work too, but yeah.
Okay, thank you.
Thank you.
Yeah.
Okay.
Lynn, can you please
I'll stop sharing now.
Lynn, can you please share your slide?
Of course. In the chat.
No, I mean, I'm asking Lean.
Yeah.
Okay, sorry.
Okay. All right. Our second presentation for today would be using machine learning to understand the built environment's influence. Um, and our presenter is Mary Azuma, if I pronounce it correctly, who is an urban planning student at Florida Atlantic University. Her academic focus encompasses various aspects of urban planning, including transportation planning, land use planning, and geospatial analysis using GIS. So, Mary, the floor is yours.
Thank you very much. Please, can everybody see my screen?
Yes.
Okay. So as you already said, my name is Mary Suman, and a graduate student in Florida Atlantic University. And today's presentation is focused on using machine learning to understand the built environment's influence on the 15 minutes transit-oriented communities. Let me put my camera on. Okay, thank you. Sure. Okay, so this is the outline we are going to follow for our presentation today. We'll look at the introduction, our background, our methods, we'll review our results, and have our discussion and see our limitations we encountered in this presentation. So this presentation explores how the built environment's characteristics around high-capacity transit stations influence local accessibility using internal trip capture as a key measurement. So in this presentation, I'm going to refer to internal trip capture as ITC. So ITC tells us the number of trips that begin and end within the same neighborhood. So if a trip starts in one neighborhood and it also ends in the same neighborhood, that is ITC. And since we know what ITC is now, we are going to talk about what high ITC means. High ITC means that neighborhoods are locally complete. You're able to start your trip and end it within the same neighborhood. And we'll ask ourselves, what is the significance of ITC in this presentation? So ITC reduces the number of vehicles on external roadways. And if the number of vehicles are reduced on our external roadways, it reduces congestion. Therefore, it helps the free flow of vehicles in the neighborhood. And also, ITC facilitates convenience. It makes it easier for travelers to complete their daily activities within a short time. And this Venn diagram helps us understand the relationship between the three key planning principles we are using in this presentation. That is the 15-minute CT, transit-oriented development, and internal trip capture. So I'm going to refer to transit-oriented development as TODs in this presentation too. So this Venn diagram shows us that 15-minute cities ensure walkable neighborhoods, and it also ensure local access to daily needs. So the 15 minutes concept is that if you want to get your essential services, you are supposed to get it within a short walk or a 15-minute walk or bike ride without using automobile. And transit-oriented development, that is the TOD, is also development around high-capacity transit hubs. So if there's development around high-capacity hubs like train stations or heavy rail stations, that is the idea of transit-oriented development. And also, the TODs ensure compact mixed-use development. And ITC, as I said earlier, is that it ensures that trip stays within the neighborhood. And the goal of ITC is that it reduces the reliance of vehicles. And these three concepts, the 15-minute city, TODs, and ITC, in this presentation all have one main goal they aim to achieve. And this main goal is to support a car-free living. So the idea of the 15-minute city, the idea of transit-oriented development, and the idea of the internal trip capture in this presentation is just to support a car-free living, that there will be a reduction of the use of automobiles in our neighborhoods. So why does all this matter? Why does the 15-minute CT, why does TODs, and why does ITC matter? As urban planners, our main goal is to create a more sustainable, also a livable neighborhood. And this concept pushes the idea of sustainability and livability within the neighborhood. Since TODs, ITCs support car-free living, if we combine them with our local access and regional access, it supports sustainability and livable neighborhood. These concepts matter to us. That's why these concepts matter to us. So together, the 15-minute CT and also internal trip capture provide a framework that connects urban form to observed travel behavior. Our project examines how the built environment and also social environment factors affect internal trip capture. Around the 96 metro stations we analyzed in Washington, D.C. and in Portland, Oregon, using the machine learning models. We came by 2 research objectives that our project intends to answer, and that is by applying machine learning tools to develop new insights into the problem of internal trip capture and the problem of the 15-minute CT. And also, we answered the question that, do different land use mix street network connectivity results the 15-minute neighborhood for surrounding high-capacity transit stations? So we gathered built environment data from various sources like US Census, NHIGS, and we aggregated it into the station level. Firstly, we created a 1-mile buffer around each of the metro stations in Washington, D.C. and in Portland, Oregon. As I said earlier, that we had 96 stations in Washington, D.C. and we had 96 metro stations in Portland, Oregon. We took each station and created a 1-mile buffer around each station. Then we gathered the built environment data and aggregated them into the station level to get data for each of the stations so we could analyze. Then we collected trip data using streetlight location database services. And a little about streetlights is that it's a very big data transportation vendor, and they calibrate modes and route-specific data into various big data formats for analyzing travel behavior. And the streetlight data uses, I think they use GPS devices, they use smartphones and other devices that with geolocation ping for their data sets. But Streetlight doesn't provide raw data. They provide aggregated data. So that was how we were able to use it to collect our trip data. And our major focus was to get the percentage of trips where both the origin and the destinations are within the same neighborhood. So on my left is the Washington, D.C. boundary, and on my right is the Portland boundary. We made sure that we included all the counties that had the 96 metro stations. So our boundary had all the 96 metro stations, and none of the stations fell outside the boundary in both Portland and in Washington, D.C. And below is a map that shows the 1-mile buffer around a metro station using ArcGIS Pro. We use ArcGIS Pro to create a 1-mile buffer around each of the metro stations. Then the hole in the middle also was created. We created a 100-meter buffer around the metro station. Then we used the erase tool in ArcGIS Pro to erase the 100-meter buffer because we wanted to take away short trips that were, or trips, unnecessary trips that were happening in the metro stations. And in order to find the best fitting model, we use this forward stepwise regression linear model to get the best fitting models. Then we use light gradient boosting machine learning model. We use the random forest, and we use the extreme gradient boosting machine learning models. And to get a better interpretation, to assess the importance and also to find important threshold, we use the partial dependency plot to assess the importance thresholds. So below is the results for Washington, D.C. And in Washington, D.C., our top predictors for internal trip capture were employment density, intersection density, and transit job accessibility. We also found a very high correlation between median income and also between transit accessibility in Washington, D.C. And transit job accessibilities correlation was unexpected in our work. So below is an employment density map in Washington, D.C. On my left, showing a very low employment density. The metro station here, this is the metro station, and the light blue showing a very low employment density. And on my right, with the deeper blue showing a high employment density in Washington, D.C. And when we come to Portland's correlation of the built environment variables with internal trip capture was higher than in Washington, D.C. And the top predictors of internal trip capture in Portland, Oregon was employment density and transit job accessibility. And also office and retail jobs were highly correlated with ITC. But none of the mixed use variables that we measured added an exploratory power to the models if we excluded employment density and transit job accessibility. So below is an intersection density map of Portland, Oregon, with the left showing the international airport and the right showing the Couch metro station, and the left showing very low intersection density. And this is due to the presence of the airports in that area, and the right showing high intersection density. So there were some similar trends in some of our results in both Washington, D.C. and in Portland, Oregon. And some were higher job density and transit accessibility. Job density and transit accessibility resulted to more local trips in both Portland, Oregon, and in Washington, D.C. And we tested some mixed use variables, and they were not strong predictors once job was controlled in both of the cities we used. And employment density, transit access to jobs, small blocks, and adult pay vehicles highly correlated in both Washington, D.C. and in Portland, Oregon. But surprisingly, we tested land use mix in 3 different ways, but none were significant in both Washington, D.C. and in Portland, Oregon. The mixed use variables showed a weaker correlation in both Oregon and in Washington, D.C. And these are our policy implications. And we recommend that stakeholders promote employment density around transit stations. This is because higher job density consistently correlates with internal trip capture. And we also encourage that there's a prioritization of walkable street design. This is because connected street grids, small blocks, enhance walkability in our neighborhood, and also intersection density and small block acres support internal trip capture, and it helps reduce the reliance on automobiles. And again, we encourage that planners should integrate shared micromobility into our planning, and which micromobility is basically the use of scooters, electric vehicles, and other other small bicycles and other ones. Most of the times, planners integrate just bicycles, but don't normally talk about scooters and electric vehicles. So at this point, we're encouraging that planners should integrate them into their plans. When it comes to the research implications, to analyze neighborhood self-containment, this research has made us know that internal trip capture is a valuable travel behavior outcome. So we encourage that if people want to measure internal trip capture or want to assess neighborhood self-containment, they should think of, if they want to assess travel behavior, they should think of using internal trip capture. And again, this project is one of the first to apply street light data services. And we encourage this because this street light data service is a big data vendor, and they enable more accurate data, and also provides high volume trip analysis compared to the traditional ways or the traditional surveys we have done in the past. And again, we are encouraging that we rethink the mixed use matrix. This is because the traditional indicators that we use showed a very weak and predictive power. So if we rethink of how to analyze mixed use metric, it is going to help us. And in future, we encourage that people should focus on, or researchers should focus on points of interest data and not just job categories. We came by some limitations in our work, and the first one is a lack of points of interest data. Points of interest, the lack of points of interest data is a very high limitation because it restricts how we can measure the mixed-use development within a neighborhood. And also, since our projects focused on just 2 cities in one continent, we cannot extrapolate our data. We cannot generalize the results for almost everywhere, since cities are different, transit networks are different, and also demographic profiles are different in different cities. We cannot generalize our results across various cities. Thank you very much.
Thank you, Mary, for an excellent presentation. Is there any question from the audience? Yes, I think we have one question in the chat box. As we have few minutes, probably you can answer here. Interesting presentation. Would you help me understand the difference between 15-minute community and ITC?
Okay, let me explain. I have my professor here, so when I finish, I'm sure he will add something to it. Okay, so the 15-minute city concept ensures that neighborhoods are walkable, and we are also able to access our essential services, that is, access our retail, we are able to access groceries and the petty things we need within a very short walk or bike ride. So people are able to access schools within the 15 minutes walk or bike ride. And internal trip capture is when a trip starts and also ends within the same neighborhood. So the number of trips that starts in a neighborhood and also end in the same neighborhood. Internal trip capture includes driving automobiles, bicycle, and also cycling and also walking. But the 15-minute city concept doesn't include the use of automobiles. That's the difference. And I'm sure Dr. Mellon will add more to it.
I was going to say 15-minute cities is a design concept. It's a concept for how we design neighborhoods. And there's various ways to measure that in terms of travel behavior. Internal trip capture is really only one way to measure it. Sometimes people measure it by mode shares. That's another way to measure it. So, it's the difference between the urban form and how we measure it with travel behavior.
Yeah, I don't see any questions, chat box. Probably I can ask a question. I know it's very difficult to find out a general factor for all areas that influence like the ITC equally, but at least based on your study, whatever areas that you considered, is there any general factor that we can say, okay, this factor is equally important in Portland, Washington?
Dr. Louise Mellon will take the question here.
Mary, you want me to take the question?
Yes, please.
Okay. In fact, employment density and small blocks or intersection density were almost equally important in our 2 study areas. And something Mary didn't mention, we picked these 2 study areas intentionally because Washington, D.C., the transportation system, the metro system's underground, and on Portland, it's streetcar, or light rail, so it's at grade. So we thought we might see different results between underground and at grade, but we actually saw quite similar results in areas. We also saw that mixed use, as Mary mentioned, all of our mixed use were based on job categories, 20 job categories. We didn't find mixed use to be significant in either study area.
Okay. Thank you, Dr. Luis. All right, Lynn, can you please share your slide?
Yep.
All right, our next presentation is on performance evaluation of 3D path planning algorithms for UAB last mile delivery application. And the presenter for this talk is Shara Ahmed. Shara Ahmed is a master's student in transportation engineering at McMaster University. Her research focuses on advanced methods for unmanned aerial vehicle operations for last mile delivery. Shara, the floor is yours.
Thanks so much for the introduction, Dr. Jahid. Let me share my screen. Can you see my screen?
Not yet.
Yeah.
Are you using
Sorry.
2 monitors?
Yes, just one
Yes,
second,
so
please.
yeah, to see which one you are sharing.
Yeah, sorry. So you can see my screen now, right?
We can see you.
Okay, thank you. So good
We can see
afternoon,
you only,
everyone.
not the slides, Sarah.
You can see me what?
We can see you in the screen, not the slides.
Oh, okay. Sorry. So sorry about that. Let me do it again. Let me share. So can you see my screen now?
Yes.
Sorry about that. Can you see my screen now?
That's yes, we can see now.
Yes.
Perfect.
Yeah. Amazing. Sorry about that. So good afternoon, everyone. My name is Sarah Hamid. I'm a master's student in transportation at McMaster University. Today, I will be presenting our research on the performance evaluation of 3D path planning algorithms for UAV last mile delivery application. This work was conducted in collaboration with Dr. Ahmed Fouda and supervised by Dr. Mutaz Muhammad. Before we begin, I'd like to acknowledge that McMaster University is located on the traditional territories of the Mississauga and the Haudenosaunee nations and within the lands protected by the Dish with One Spoon, One Palm agreement. Let me quickly walk you through the agenda. I will start with a short introduction, then move on to the background and aim of the study. After that, I will cover the data case study and methods we use. Then I will present the results, and finally, I will wrap up with our main conclusions. Starting with the introduction, in recent years, unmanned aerial vehicles or UAVs has increasingly been explored as an applicable solution for enhancing last mile delivery in urban logistics. The final segment of the delivery process is widely acknowledged as the most expensive and operationally complex, often contributing up to 28% of the total logistics cost. UAVs offer several benefits, including improved delivery speed, cost reduction, and minimize environmental impact, particularly in densely populated or remote areas. As shown in the figure, which presents a scope bus index publication data, research on UAV-based last mile delivery has expanded significantly from just one paper in 2015 to 44 papers in 2024. This upward trend highlights the increasing attention from researchers toward optimizing UAV applications in urban delivery systems, driven by advancements in technology and the rising demand for efficient, sustainable logistics solutions. Moving on to the background and aim of this study. To ensure UAVs operate effectively in real-world environments, we need path planning algorithms that are both robust and efficient. In particular, 3D path planning algorithms are considered fundamental for successful deployment of UAVs. In the literature, 5 main algorithms are commonly used: Dijkstra, A-star, particular swarm optimization or PSO, genetic algorithm, and rapidly exploring random tree star or RRT star. Each of these algorithms offer various trade-offs between computational efficiency, adaptability, and solution quality in complex environments. To understand the research gap, a systematic comparison of previous studies is presented. Most studies use simplified 2D environments lacking real-world 3D complexity. Researchers focus on individual algorithms missing trade-offs between exact and heuristic methods. Most prioritize path length over practicality. Many studies on UAV path planning use overly simplified environments, just as 2D grids or obstacle-free simulations, reducing their relevance for real urban last-mile delivery. The focus has often been on analyzing single algorithms rather than directly comparing exact algorithms like Dijkstra and A-star with heuristic methods just as PSO, genetic algorithm, and RRT star. The evaluation metrics used are generally limited, with an emphasis on minimizing path length while overlooking factors such as computational efficiency and practical feasibility. This study addresses two main research questions. First, how do different path planning algorithms perform in real-world 3D environments in terms of path length and computational efficiency? And second, what are the trade-offs between exact and heuristic methods, and which approach best balances efficiency and practicality for UAV delivery? Next, the study's data, case study, and methods are presented. Okay. This study investigates UAV path planning in downtown Toronto using detailed 3D urban data sourced from the City of Toronto Open Data Portal. The environment is modeled as a 3D dimensional grid measuring 630 meters by 550 meters by 290 meters, representing a sizable urban area with a UAV flight altitudes restricted from between 30 and 120 meters in accordance with Transport Canada regulations. This figure illustrates the 3D OpenStreetMap model of downtown Toronto used in the simulation, highlighting the complexity of the urban environment considered in this study. We started by pre-processing the building's data, removing any structures with zero height and filling in missing values. Then we tested 5 path planning algorithms, Dijkstra and A-star, with line of sight, along with PSO genetic algorithm and RRT store, all implemented in Python and run on cloud computing infrastructure. Our system converts Toronto's building data into a 3D navigable space and calculates optimal routes that avoid obstacles while following aviation regulations in these dense urban environments. We enhanced Dijkstra and A-star algorithms with line-of-sight adjustments to ensure obstacle avoidance and compliance with aviation rules. In 3D, each vertex connects to 26 neighbors, which allows for more flexible and efficient path planning. Our methodology includes 5 main steps. First, we created a 3D grid map of downtown Toronto using OpenStreet data and added obstacles like building and no-fly zones. Second, we defined the problem by setting the start and goal points, specifying path objectives and constraints, and selecting key performance indicators or KPIs like path length and computation time. Third, we selected 5 algorithms like Dijkstra and A-star with line of sight along with PSO genetic algorithm and RRT star. Fourth, we performed simulations for each algorithm and tracked their performance. Finally, we visualized the resulting paths and compared all algorithms based on the defined KPIs. Moving forward, we present the results. Starting with the exact approaches Dijkstra and A-star, Dijkstra produces the most direct path, but is computationally expensive. A-star offers a path similar to Dijkstra, but with reduced computation time. Heuristic method like PSO is faster than Dijkstra and A-star, but had slight path deviations. Similar to PSO, genetic algorithm offers a faster path, but more deviation compared to PSO. RRT star is the fastest, but had the longest path. By considering all of these algorithms together, we compare the trade-offs between their performances. Dijkstra and A-star both achieve the optimal path length with zero deviation, but A-star is faster and generates smoother paths. Heuristic methods prioritize speed over precision. RRT star is the fastest but has the longest path, while genetic algorithm offers a balance near optimal length, moderate speed, and the smoothest route. PSO falls between these methods in terms of speed and path deviations. Altitude variations remain consistent across all algorithms, indicating that environmental complexity impacts them similarly. In terms of path length, Dijkstra and A-star with line of sight achieved the shortest path and most precise routes. Heuristic algorithms such as PSO, genetic algorithm, and RRT star produce slightly longer paths because of their probabilistic search nature, resulting in minor deviations. When it comes to computation time, RRT star was notably faster than Dijkstra, offering a significant speed advantage. Similarly, A-star, P-star, and genetic algorithm also demonstrates much faster execution times compared to the KESRO, highlighting the efficiency benefits of heuristic approaches. Now we wrap up with our conclusions. This study presented a comparative analysis of 5 path planning algorithms, the KESRO, A-star, PSO, and genetic algorithm, and RRT star, for UAV navigation in a 3D urban environment, evaluating their performance in terms of path length, computational efficiency, and flight smoothness. For applications requiring optimal path solutions and where higher computational effort is acceptable, the KESRO and A-star are recommended. When a balanced trade-off between computational speed and flight smoothness is desired, with an emphasis on stability, PSO and genetic algorithm are appropriate choices, with genetic algorithm particularly suitable for stable flight operations. In scenarios prioritizing minimal computation time over path optimality and precision, RRT star is the most effective algorithm. Future work should focus on quantifying energy savings from smoother paths, developing high-fidelity energy models, and conducting real-world flight tests and designing adaptive energy-aware planning algorithms. Overall, this study provides a practical benchmark for UAV path planning, emphasizing the importance of integrating smoothness and energy efficiency in future autonomous UAV systems. Thanks so much for your attention. I'm happy to answer any questions. To learn more about our MITL Research Lab, please scan the first QR code for more information. Also, you can also connect with me on LinkedIn or via email. Thanks so much.
Thank you, Sarah, for your interesting presentation on a timely research topic, especially when given the congestions and the delays in last mile delivery. I think we have a good amount of time for question and answer. If anybody wants to unmute and ask questions, please feel free to do that. Or you can also write your question in the chat box. All right. In the meantime, Sarah, I think I can ask you a question.
Sure.
So can your model, so this UAV, there might be many restrictions in the air, where you can go, where you can't. For example, if there is any restricted area, say defense area, that where UAV cannot fly, or wherever plane take off or land. So those are the restricted area. Can your model recognize those types of areas, and UAV can avoid those when you are optimizing their path?
Yes, sure. Actually, when we are doing our environments, we are selecting like it's a real world environment. So there is some buildings you fly above of this building, but some of them it's restricted. It's no fly zone, so you have to avoid this building. So it depends on your constraints for the obstacles. If your obstacles, some of them you can fly around or above of these buildings, and some of them you have to just avoid them. So it depends on your obstacles and your constraints.
So this is what you do with the blocks in your 3D space.
Yeah,
blocking those
exactly.
specific blocks that kind of meet those criteria. Say no flying zone, something like that.
Yeah, no flying zones like airport zone or any other like any areas we can fly above these areas or around these areas. So you have just to define your constraints for the algorithm, and after that it will work. Like in our building, in our OpenStreetMap, we define all the buildings, and some of them, like according to Transport Canada, we can't exceed the. Our limitation is from 30 to 120 meters. So we can't exceed any of these meters, and this like the same as you said, like it's no fly zone. So it's the same. It's our constraints for these areas.
Okay. All right. Thank you. If there is no question, we can jump to the next presentation. Lynn, can you please share your slide?
Sure.
Thank you.
Thanks so much.
Okay. So our next presentation is on Is the Sky the Limit? Understanding Consumer Adoption Dynamics of Electric Vertical Takeoff and Landing Aircraft. Our presenter is Marvin Griffinstein. Let me see if I have any bio for.
Yeah, maybe
Marvin is
you
a
have a
visiting
bio?
researcher in the Department of Urban Studies and Planning at Massachusetts Institute of Technology. So Marvin, the floor is yours.
Thank you. Thanks for the introduction. And I know it was a timely shift because my colleague Paula Pradl, who should present the work, can unfortunately not do so. So I will take it over.
Perfect.
1 second, I will share. Okay, can you all see my screen?
Yes, we can see your slide.
Perfect. All right, then I'll start off. So thank you for the opportunity to present our recent research work. As stated, it's from Paula Pradl and myself. And we conduct a study on consumer adoption dynamics of eVTOLs in the DACH region, so in Germany, Austria, and Switzerland, and applied the UTAUT 2 model to this emerging field. So let's just hop into our motivation. So what motivated us to look in such a nascent technological field? So eVTOLs, that's the short for electrical vertical takeoff and landing aircraft. They are widely seen as a future cornerstone of urban mobility. Why is that? Because they are fast, they are low emission because they're electric, and very space efficient because they can use the vertical airspace. And with a projection market size of roughly $500 billion by 2030, the economic momentum is certainly undeniable. But there's one question that remains quite central, and that's will people actually use them? And also that is beyond technical feasibility, what determines consumer acceptance, basically. For that, we looked into the literature and also in theories that look into user adoption, consumer adoption, intention to use behavior, and all that. While urban air mobility has gained traction in policy and engineering circles, research on end-user adoption, especially of pilot-operated eVTOLs, and also in the DACH region, it remains very scarce. To address this, we basically decided to employ the UTAUT 2 model. It's a leading framework for explaining consumer technology adoption. It basically came from a theory of recent action, which got extended to technology acceptance model, TBB, and then to UTAUT and UTAUT 2. And after that extension, we came up with that structural research model. We did one small adjustment. We put trust as an independent variable also into our model, because we believe that trust can add on to the constructs from the UTAUT 2 model. For that, we had a data collection. The population as stated was from Germany, Austria, and Switzerland. The timeline for the data, so it's a quantitative survey-based data approach that we had. We collected it via a dual sampling strategy, first a convenience sample, and then over prolific, we went on a quota sample, especially for gender, to get a gender split among all the countries. It was roughly 1 month, the data collection procedure. And then after it, we collected 433 responses. However, there were certain dropout amounts and then also careless responses that didn't take the right control questions, or there were missing values and so on. So after removing all the careless responded, it left us with 320 valid responses from individuals in Germany, Austria, and Switzerland. These are the socio-demographics. As you can see, they are from a gender perspective quite good looking. And then while the responders are mostly, we have an over amount of young people and professional white collar people. However, that would also align with what we saw as early adopters of these technology. What we did now is we used a confirmatory factor analysis because maybe that I forgot to mention that. So when we did the data collection, we had an online survey with 42 items adapted from established scales from Venkatesh et al. That have basically the adapted scales of all the constructs that we have of performance expectancy, effort expectancy, and so on. And then in this step here, we basically demonstrate that all constructs are high internal consistency. So the Cronbach alpha is bigger than 0.9. So the confirmatory factor analysis results confirm basically convergent validity with most factor loadings higher than 0.8, and also the model fit, which is very strong. So after having confirmed the model fit, after the model fit and confirmatory factor analysis, we are able to do a structural equation modeling. We choose the partially square structural equation modeling, short for PLS-SEM. And after using the PLS-SEM with a 5,000 bootstrap sample as suggested by Jahedul, we tested all hypotheses in our entire structural model that we have showed, and 6 out of the 9 hypotheses were supported. So the key findings that we have is the performance expectancy was the strongest direct predictor of behavioral intention, followed by hedonic motivation and social influence. What does that mean? So performance expectancy is basically how good is the performance of the product that I'm going into so of the eVTOL, but also how good does that fit with my daily life? So that's also a performance expectancy aspect. And then hedonic motivation is how fun is it to ride an eVTOL? How entertainment is it? And social behavior or social influence is, sorry, I went too far. Social influence. So SI is basically what do others or peer groups or friends of mine think should I use eVTOLs? So these 3 constructs were basically the constructs with the strongest direct predictor of behavioral intention. Trust had no direct effect on intention, but strongly influenced by performance expectancy. And then effort expectancy, facilitating condition, they were non-significant. And the model explained 57.6% of the variance, so our R-square is 0.576. So that comes to our discussion and contribution. So I already talked a little bit about the discussion. So the findings confirm basically the relevance of the UTAUT2 model in this novel context. And they highlight 2 core insights. Trust shapes perception. So trust in the safety and technology directly shapes adoption by performance expectancy. So not directly, but indirectly via performance expectancy. And consumers are not irrational. So they want to understand how eVTOLs benefit them concretely. That's why performance expectancy was so strong positively strongly correlated with behavioral intention. The insignificance of facilitating conditions in our effort expectancy is likely, that's what we said in the discussion, is likely because of the nascent stage of the technology and there's no real world usage that has begun. So that's why maybe ease of use of a technology concerns remain maybe a little bit too abstract. And based on our results, we also propose for research policymakers, but also for providers, some implications, how they can practically market or communicate their benefits of the eVTOLs. For example, they should include demos, safety reports, and also what's good is that they should use some kind of, for example, influencers or communicators, testimonials, or that kind of show the social proof, because social influence was a big construct that influenced behavioral intention. Yeah, and then at the same time, our contribution is also theoretically. So from a theoretical lens, we extend the UTOL2 model in the eVTOL space, adoption space, which has not been done before, and applied that in a very under-researched transport technology. Yes, and that would be from my side. Thank you.
All right, thank you, Marvin, for these presentations. And I think we have some questions in the chat box. One is from me as well.
Yeah.
If you can answer those questions, because we have a few minutes, you can probably,
yeah.
use the.
Let me. I can't see the.
Yeah. So my one is: are we ready for the kind of electricity we may need for eVTOL operations? Because it will put a pressure on the electricity, right? So, do we have any idea, like what?
Yeah, I can't really see the comment. Can you maybe read it and then?
Yeah. So, are we ready for the kind of electricity load we may need for eVTOL operation?
I mean, we also did an others. It was just a short study, so we also had contact during that study with two German companies. One failed Volocopter, and the other one, Lilium, still being on the market, regarding what's their early adopter user groups. So when we technically speak about their early adopter user groups, it's probably going to be businessmen who have a company who want to kind of cut emissions, and that's why they use eVTOLs from getting from, let's say, New York airport to the city, because the prices will be still high. So I think from an, let's say, when we talk about energy consumption, it's still at the beginning state, I would say, rather low, because it's an highly expensive service at first, when it's not in scale and so on. So probably, my opinion is, it doesn't really have a big effect at first. But I also think they're not quite efficient in use. It's just, yeah, they would need to have solar or wind energy for their battery packs, because otherwise I think it would be too expensive. Yeah.
Right. And we have another question. Have you ridden from Dr. Louis Merlin? Have you ridden in a eVTOL yourself? And if so, what was your experience?
No, unfortunately, I didn't have the chance to ride in it myself, and that's also, I would say, one major limitation that we have for that study. Obviously, I mean, we gave the survey respondents an idea, because we can share pictures with them of very nicely looking eVTOLs, but also like, let's say, real world pictures, because there are Volocopter and Lilium vehicles out there that are close to commercial state, but there's almost none in that region, or there is none in that in the DACH region, which really is commercial offer, or which is flying currently. And yeah, myself, I unfortunately didn't have the chance yet. Still need to do that.
All right. I have one last question for you, Marvin. So participant that in this data collection process, they don't have real experience with eVTOL, I guess, and then so the responses will be kind of from their imagination. So is it possible that we can bring virtual reality to immerse participant and ask questions after the experiment?
Yeah, exactly. As I mentioned, it's a huge limitation. I mean, these user adoption theories like TAM, UTAUT, and so on, they are great, but they work, but if it's always difficult if you have a technology which you cannot use. And for example, I'm doing personally a lot of research on autonomous vehicles myself as well. And with these vehicles, we come to a state where we can actually commercially write them. So doing these kind of studies now, it's different to doing them 10 years ago when the research field started, because it was exactly the same problem back then. But I think the academic research world needs these kind of studies because the perception of people change. And what we have learned is that trust and safety issues are not a big deal when it comes to commercial offerings anymore. And we saw that in this study here as well, that trust didn't have a direct effect of behavioral intention, right? So yes, they are from the imagination, and yes, that's a big limitation. And also, yes, I think the possibilities that Dr. Jahed, you have mentioned with the VR technology and so on, that I think these are good solutions to come closer to actual commercial states. There are a lot of ways to get closer. You can also do Wizard of Oz studies, like you can put the people into a real eVTOL that's on ground and say to them, imagine you would fly in such a case, what would you feel, and so on. I think these are all studies that we could do future research on to explore more of this user adoption. Yeah.
Okay, thank you, Marvin, for shedding some lights into this emerging technology. And we'll now jump to our next presentations.
Thanks a lot.
Lynn, can you please? Yeah, thanks a lot. Lynn, can you please share your slide? Okay, our last presentation for this session is how would urban and regional air mobility affect relocation decision? And we'll play a recording for these. And I think one of the co-authors, Javier, will be here to answer any questions that you may have after watching the recording.
Please let me know if the audio not works.
Hello everyone, my name is Mingzhe Xu, and today I'm going to present our recent work, Urban and Regional Air Mobility and Relocation Decisions in the United States. It starts from a machine learning supported path analysis. So here is today's content. So I will first briefly introduce the background and the methodology and results and takeaway and Q&A session. So background. So as you can see from the title, so we are focusing on the URAM today. So urban and regional air mobility is an emerging field in transportation, typically involving the use of electric vertical takeoff and landing aircraft, also known as air taxis or flying cars, to enable the movement of people and goods within urban and regional areas. URAM's high speed approaching 140 miles per hour could significantly reduce travel times and benefiting daily commuters. Additionally, URAM could improve access to work, healthcare, and education, especially in rural or remote areas. This increased accessibility might influence where people choose to live and work, reducing the constraints of proximity, provided that URAM services that are safe, accessible, and affordable. But by checking previous literature, we found that most of studies only focusing on interest in using URAMs, but just rare study focus on the relocation decisions, or just the URAM impact on relocation decisions. So based on the background and gaps, so we just proposed 3 different research questions. Which factors affect people's interest in using URAM services in the nationwide US? And which factors affect people's relocation decision considering the usage of URAM services? And is there a behavioral pathway among contributing variables interest in using URAM services and relocation decision making? So to answer these research questions, our study uses path analysis to connect models of URAM perceptions with relocation considerations and examining how social economic characteristics and travel behavior influence the perceptions. So This is a survey-based study, so we conduct survey on Qualtrics, and we also deliver the survey via Qualtrics. So there are three major parts on in the survey. The first is basic background, which includes some social demographic questions, and then it's travel behavior, which we can collect some data about people's commuting behavior, and also the URAM perception, on which we can get data about sorry, people's perception on URAM services. So we launched this survey in February 23, and this is a nationwide survey in the United States, and we got in total more than 2,000 samples, but after the data cleaning, we got only 1,047 samples. And in this survey, we have two key questions. The first one is, are you interested in using URAM services, which is a Likert scale question. But for the modeling purpose, we just recode this to a binary variable. And then is, if your new job's commute time exceeds your maximum tolerable limit, would you consider using URAM services to commute to avoid relocating? So this just yes or no. And here we just show some preliminary view of our survey data. So you can see from those pie charts, more than 60% of people, they didn't have any awareness of URAM or VTOL concept, and most of people, they at least somewhat interested in using URAM services, and more than 85% of respondents, they said, okay, they are willing to use URAM to avoid relocation. And then if you take a look at the bar plot on the right-hand side, so you can find that this is about the concerns about riding in a VTOL aircraft, and the blue one is safety, orange one is cybersecurity, and privacy one is, gray one is privacy, sorry. And so it's very clear that safety is the top one concern. So that's the most important part people care about if they will use your URAM services. So these slides show a very detailed framework of the path analysis we use in this study. So here we have two sets of models. The first one is models for interest in using your URAM services, and second one is models for relocation decisions. So we will, based on these two sets of models, we can directly know the relationship between factors and the dependent variable, which is, interested in using URAM services and relocation decisions. But if you want to know the behavior, if the behavioral pathway exists or not, so we need to estimate the indirect impact, and we need to check the direct impact first and then estimate the indirect impact, and then we can calculate the total impact. So for the direct impact, is just the marginal effect on the dependent variable directly. But for the indirect impact, since we put the interest in using URAM in the relocation decision model as a like median variable, so that means if people can directly impact on different factors can directly impact on the interest in using URAM, but the interest in using URAM can directly impact on the relocation decisions. That means those factors can impact relocation decisions indirectly via the interest in using URAM services. So we just use the marginal effect of interest in URAM services on relocation decisions times the marginal effect of factors on interest in using URAM services. So then we got direct and indirect impact. We just add them together, we got the total impact. So for the marginal effect, we just use partial dependence to estimate that. So since all the independent variable in the study are categorical variables, so we just pick a base variable and then we just estimate if the category change, so how the predicted probability will change. So that's a margin effect in this study. And also you can find that we use different machine learning methods, but since all models are wrong, but some models are useful. So that means all models, because of their unique mechanisms, they will have their own attributes. So they will have different bias in different ways. So, but we cannot simply say simply to identify the bias. So we decided to average them together. So we estimate the margin effect for every model, and then we just, for each factor, we remove the highest and lowest margin effect, and then we still have 3 margin effect, and then we average them as the average margin effect in this model, which is also the direct impact. So before we do the modeling part, we just quickly check the sample distribution. And the first table shows the cross distribution of interest in using URAM services and URAM related relocation decisions. So we can find that if people are not that interested in using URAM services, they will more likely just reject to use URAM to avoid relocations. But if people are interested in using URAM services, they are more likely to just use URAM to avoid relocation. And the second table shows a correlation matrix between dependent variables. As I introduced before, so for modeling purpose, we just code the interest in using URAM as a dummy variable. So we have 2 dummy variables now. We can estimate the Pearson R's. And so the correlation is 0.44. That means a moderate relationship between 2 dependent variables, which is interest in using URAM services and using URAM to avoid relocation. That means the behavior pathway should exist among factors and interest in using URAM services and using URAM to avoid relocation. Then we just fit the machine learning model and estimate the marginal effects. And then here shows the direct impact of interest in using, of factors on interest in using URAM services. So the blue arrow means negative impact and the red arrow means positive impact. So it is very clear that age, gender, and household size, and also land use pattern and commuting type are negative impact on interest in using URM services. But high income, household with children, people, those have technical job, and frequent air traveler, those with helicopter experience, those no UAM concept before they take this survey, so they were more likely to interest in using URAM services. And this slide shows the results, the direct impact of factors on willing to use URAM to avoid relocation to avoid relocation, sorry. And still, blue one is for negative impact and red one is for positive impact. And people are older than 46 years old, and people who lived in the very large household and who lived in a rural town area and who commute by carpooling will less likely to use URAM to avoid relocation. And high income householders and people who have a technical job and who remember flying car movie and frequent air traveler and who have a really long not that high longest acceptable commute time, and who are interested in using URAM services, who feel congestion is a problem, who knows URAM concept before they take this survey, are more likely to use URAM to avoid relocation. And you can see this one, I mean, the direct impact of interest in using URAM services on relocation decision. The impact is 23.69%. That means compared to those who are not interested in using URAM services, those interested in using URAM services are 23.69% more likely to use URAM to avoid relocation, which means the pathway is really strong here. And this slide shows the path analysis. We didn't put all the path analysis result here since it's a really large, actually it's a really large table. So, but this figure just shows some patterns, very common patterns in the path analysis here. So first you can see, for example, the 18 to 25 years old people. So the direct impact of on relocation decision is negative 1.92, and the indirect impact is the dashed line is negative 1.24%. So both of them are very small impact, but if you add them together, so the negative impact become negative 3.15%, which is kind of high and cannot be ignored. And also, if you take a look at the positive impact, the household with children show the same pattern. That means two small positive impact, they add together, so the total impact is not that small. So you have to pay attention on this impact. But also there are a contrary example, which is helicopter experience. So the direct impact is negative, but the indirect impact is positive. So you add them together, the impact actually being was eliminated, and it's very close to zero. So that means if the behavioral pathway exists, you have to take a look at the indirect impact. Then you can know the total impact, and to make the correct decision. And takeaway. So this study conducted a national survey regarding urban and regional air mobility and individuals' relocation choices considering URAM. And the behavioral pathway exists among variables interested in using URAM services and relocation decision considering URAM. And males, high-income householders, and those with technical jobs, and air travelers, and those familiar with URAM were more likely to be interested in using URAM services. And interest in using URAMs was found to be affect individuals' relocation choices considering URAM significantly. And that's all about today's presentation. So if you have any questions or you are very interested in our study, please just feel free to contact me or my advisor, Dr. Junliu. And also, since this paper is published on transport policy, so we generate a QR code. You can just scan this one and to access our paper. And yeah, that's all for today. And if you have any questions, you can ask my colleague Javier or just send an email to me. And thank you very much.
All right. Excellent. So I think Javier, a PhD student in the University of Alabama, he's answering questions. Already answered one question in the chat box. Any question from the audience, please feel free to unmute yourself and ask questions. Javier will be happy to answer questions. All right, I think that would that concludes our session, and I thank you everyone, especially our presenters, to give talks on those nice and interesting topics, and it was wonderful having you here. So for the next sessions, I'm going to type in the chat box what is coming in I think 1 p.m. right? Yeah.
Yeah.
So
I can
this will
copy
be
all the afternoon session and share in the chat box.
okay. Yeah, I think I did one, but it's it looks like I have more characters than the limit. So if you can just probably put some links here so that people can join in their interested session. So I think this Zoom room also features session 16, I believe, right?
Yeah, session
Yeah.
16.
So that'll be starting at 1 p.m. CDT. So feel free to join back when the session starts. So Lynn, what we do, we conclude the session now here?
I think I need to like transfer the tech stack to my colleague.
Okay. Right. All right. Thank you, everyone.